All right, so chapter 19, guys, chemical thermodynamics. If you look back at the title of chapter 5, it was thermochemistry. What's in chapter 19, first of all, I don't think there is anything in this chapter that you will have seen before. I don't believe there is anything taught in Chem 1 in this chapter. However, that doesn't mean that it's going to be incredibly difficult. We're actually going to see a number of processes that we used in chapter 5 that we will use again in this chapter, just in a slightly different setting. Thermodynamics differs from thermochemistry in that this word involves a little bit more of like a physics spin to it, just a little bit. For any of you that are going to pursue engineering or you're going to apply to an engineering school when you go off to college, you will take a full year course in thermodynamics. Okay? So, the first thing that's going to come up in this chapter, and honestly you're going to be asked this really throughout all of chapter 19, is you will be given a situation, a process or a chemical reaction. You'll be given some information about it, and the question will ask, is this process, is this reaction spontaneous or not? Now, what do I mean by spontaneous? Okay. When I say spontaneous, I mean, will this reaction occur without any outside intervention, without any help in any way? Will it occur on its own? Okay, and let me just give you a very, very simple example. Okay, if you release a ball on a downward slope, the ball will roll down that hill spontaneously, meaning on its own. You don't have to do anything. Once you release the ball, it will roll down the hill on its own. Okay? Things do not move uphill on their own. Okay? Think physics. Okay? How do you get any object to move uphill? What do you have to do? Apply a force, push it. Okay? Something that is not spontaneous will only happen if you expend some energy to help it along. Okay? You will be asked, will this reaction or this process, whatever it is, will it occur on its own? Yes or no? Let's talk a little vocabulary here. For some reason, the College Board does not like this word, spontaneous. Okay? They are not likely going to ask you, is this process spontaneous? What they will ask is a slightly wordier version of that. They will say, is this reaction thermodynamically favored? Okay? They mean the same thing, okay? It means, is this a reaction that will occur without any outside help? Try your best, and I will too, to use this phrase instead of the word spontaneous, okay? And I'm going to try to be a good model for you and use that phrase instead, okay? Because that's what they prefer. Now, one of the things that's going to help us predict whether a reaction is favored or not is a concept called entropy. Please, guys, don't mix that up with the word enthalpy. They're similar and they mean two totally different things. What does enthalpy mean? Heat energy. Okay? Entropy means something quite different. You can define it multiple ways. First of all, it's abbreviated with a variable. It's a capital S. Entropy, you can define it disorder, randomness, chaos. I will very often use the word messiness. Okay? Entropy means disorder. And let's first talk about this concept entropy, just in terms of states of matter. Okay, if you guys will, turn around and look at the models that I have on top of the cabinets up in the back of the room. Those are models of different solids. Would you say that those models, doesn't matter which one you're looking at, would you say that those structures look organized to you? Like they have a repeating pattern, do you think? Yeah, they do. Okay. Solids in general, if you were to look at a solid on like at the atomic molecular level, solids are very organized, they're very tightly packed. They do have some entropy, some disorder, but very little. Solids are considered very organized, low entropy. Liquid state has a little bit more entropy. Okay, liquid particles are still bonded to each other, but they're not locked into these rigid structures. Liquids can flow, so liquids have a little bit more entropy. And you'll notice here I've used this greater than symbol twice to mean gases have an incredible amount of entropy. Gases are wild, they're crazy, their particles are far apart from one another, they're bouncing off the walls. Gases have the highest amount of entropy. Okay? And I'm going to say something that's going to sound a little bit philosophical, a little deep thought, maybe a little strange. The universe favors increases in entropy. Let me say that to you another way. Our universe likes things to get messier. All right? And I'm going to give you an example. We're going to do a little visual exercise here, which I think you'll enjoy. So here's what I want you to do. And play along with me. I want you to close your eyes. Stop writing, put the pencils down, close your eyes. Right. Okay, I want you to visualize what your bedroom looks like right at this very moment. Okay? Are you picturing it? Are there clothes on the floor? Is your bed made? If you have a desk in your room, are there papers and books everywhere? Okay. All right, open your eyes. Now, everybody's a little different in how neat or tidy or messy they keep their room. Everyone's different, but I'm going to give you a little hypothetical exercise here, and I think you'll enjoy this. I want you to imagine that for 30 days, so about a month, you don't ever do anything to tidy up your room at all. And I know what you're thinking. I already go 30 days and I don't tidy up my room. Wait just a second. We're going to take this down a disgusting path. Okay? Yeah, you're going to love this. Okay, so what I mean is, in 30 days, you don't ever pick anything up off the floor. You don't ever fold anything. You don't hang anything up on a hanger. You don't do laundry for 30 days. You don't make your bed. I mean, you don't do anything to clean your room. You don't even put things in the trash can. If you need to blow your nose into a Kleenex, that Kleenex just gets dropped on the floor. There it is. Yeah, gross. Okay, but let's go even grosser. Let's say you're a person that brings food into your room. Okay, I personally do not, but some people do. You know, let's say it's 2 a.m. You get that craving for the late night refrigerator pizza. Sounds pretty good around 2 a.m. Okay? You bring a slice of pizza up to your room, and about 3/4 through the way through that slice, you think, yeah, you know what? This really wasn't as good as I thought it was. I'm not going to finish it. So that quarter slice of pizza is staying in your room for 30 days. Yeah, it's only a matter of time before the critters show up. Yeah. There's like a whole cockroach colony that's making their little habitat in your room. And let's be even more gross. Yeah. Okay. You have a bathroom attached to your bedroom. You don't shower for 30 days. You don't brush your teeth for 30 days. Are you ready? You don't flush the toilet for 30 days. Okay? All right. We're talking about, like, people in hazmat suits are going to have to come and rescue you out of your abyss of filth. All right? Here is the point I am trying to make. If you make zero effort, things get messy, okay? The universe favors an increase in entropy, an increase in messiness. How do you stop that process from happening? You have to expend energy. If you don't, things get ugly. In order to stop that, you have to expend energy. It takes energy to bend over and pick something up off the floor. It requires energy to run the vacuum cleaner. It requires energy to flush the toilet. Okay? So, whether you all are aware of it or not, we are all constantly fighting this battle that entropy is increasing. Okay? And if we don't expend the energy, things get ugly in a hurry. Okay? So just kind of keep that thought in the back of your mind. We'll come back and visit this whole universe's tendencies in just a moment. But the first thing that I'm going to ask you to do, and you'll see this a lot in multiple choice, is you'll be given some real life situations, you'll be given some chemical reactions, and you are supposed to predict what is happening to the entropy. Is it increasing? Is it decreasing? Okay, and we're going to do these together. And let me just kind of walk you through the thought process. Okay? Let's look at this first situation. It says a cube of sugar dissolves in hot tea. The first thing I would ask myself if I'm doing this question, if I'm reading this question, is this situation getting messier or is it becoming more organized? What do you think? It's getting messier. Okay? You had a nice organized compact cube of sugar and now it's all dissolved. That's getting messier. Does that mean entropy is increasing or decreasing? Increasing. Okay. Well, what I'm asking you for here, guys, is what is the sign of delta S? Is it positive or negative? If entropy is increasing, what is the sign of delta S? Positive. Okay. And increasing entropy, does the universe like that? Yes, it does. Okay. How about this second one? A lake freezes over in winter. What do you think? Okay, defend your answer. She says decrease. Why? It's going from liquid form to solid. That's becoming more organized. Okay. Rainwater on the pavement evaporates. What do you guys think? Increase. Defend your answer.
The rainwater goes from liquid to gas.
Liquid to gas. Okay. Liquids have a certain amount of entropy, but gases have a lot more. Okay, let's look at some actual chemical reactions this time. Solid lead plus gaseous oxygen leads to lead oxide solid. What do you think? Kevin, what do you think?
I think it's going to decrease.
Okay, correct. Defend your answer.
On the left, we have a gas, which has high entropy, and in the products, we have no gas, so there is a decrease.
Okay, so he's looking at it from the perspective of we have a gas on the reactant side, gases have high entropy, we have no gas on the right. You could also look at it from the perspective of two things separated are combining into one. Synthesis reactions, not always, but most synthesis reactions where you have one product will very often have a negative delta S. Okay, how about this one? What do you think?
Decrease.
Okay, you're right. Why?
Because there's two particles, in reaction.
Okay, so two reactants combining into one. In this particular case, we didn't have different states of matter. Everything was a gas. You could look at it from the perspective of what he said, this is becoming one thing, or you could also look at it from the perspective of we have 1, 2, 3 moles of gas on the left and only 1 mole of gas on the right. Gas is high entropy. There's more high entropy on the left. Last one, what do you guys think? Increase. Okay? This is chemically written out what the process of dissolving is. Okay? This would be very similar to this one right here. Okay? So you may be asked to do this on multiple choice. You may be asked to do this on free response as well. You know, what is the sign of delta S? Defend your answer. Okay, now, here's the thing. As I started off telling you today, you will be asked many times, here's a process, here's a reaction. Is this reaction favored, yes or no? Well, guys, if your delta S, for whatever that process is, if your delta S is a positive number, then you can say this is probably favored. Okay? Positive delta S's usually indicate something that is favored, something that is spontaneous. Please notice I don't use the word definitely. I'm only using the word usually, probably. We will see in just a minute. How do you answer the question with not usually or probably? We'll get to that in a second. If your delta S is a negative value, it is probably not going to be favored. It doesn't mean it definitely won't be, but it is unlikely to be favored for the reasons we just described. Okay. Now, how do you make a decision where you know for sure whether something is favored or not? How do you know when you can stop using the words usually, probably, likely? Here's how you can know for sure. You are going to calculate something called Gibbs free energy. If you would take out, please, your equation sheet and look on the back. Under that thermochemistry section. In that section, look at the 1, 2, 3, 4, 5th equation down. You should see an equation that looks like this, although my apologies, I forgot to include the little degree symbols like it is on here. Just to review, do you remember what the little degree symbols mean? Do you remember? Yeah.
Standard.
Standard state, yeah. Okay. But in general, this is the equation, and guys, Gibbs free energy is delta G. Okay. We know what delta H is. What is that? Change in heat. What's the fancy word? Enthalpy. Okay, what do you think T is? Temperature. And then we've just learned this one today. That's change in entropy. Okay, so here's the point. How do you answer for sure, for certain, is this reaction favored or not? You calculate a number for delta G. Let me say that to you another way. The only reason you would ever need to calculate a number for delta G is to answer the question, is this favored, yes or no? No gray area, just is it or isn't it? And here's how you answer that question. If you calculate delta G and it comes out to be negative, then that means for 100% certainty, yes, this process is thermodynamically favored. If delta G comes out to be positive, then the answer is no, it is not favored. Please notice, guys, I am not using the words usually, probably, likely, Delta G, there's no predicting, there's no probably, likely, there's none of that. It either is or it isn't. Delta H and delta S, looking just at those we can make predictions and say it's probably going to be favored, but delta G we can know for certain. So, let's get to a calculation. I've given you a reaction, very simple one. I've given you delta S, I've given you delta H, and then the question says, it's really 3 questions in one. Is this reaction favored? Now stop there. Anytime you are asked, is this reaction favored? And you have numbers to work with, what are you going to calculate? Delta G, okay? Is this favored at 10 degrees, 0 degrees, and negative 10 degrees? You're going to calculate delta G 3 times with 3 different temperatures. Be careful with your units. Go. Use that equation we just were looking at. Okay. So, ladies and gentlemen, the question was, is this process favored at these 3 different temperatures? So, here's the first one. What's the answer? Is it favored, yes or no?
Yes.
How do you know that?
Negative.
Because delta G is negative. How about this one?
Yes.
Yes. Okay, and this one?
No.
No. All right, so if this was a free response question, you would need to show that calculation and then make just a very quick statement. Yes, the process is favored because delta G is negative, something like that. All right. Now, I'm going to say something that's going to annoy you. You could have answered those questions without doing any calculations whatsoever. God! Now you tell us. Let me show you. Look at the reaction that's going on. Oh. Ice is melting. Why, ladies and gentlemen, could you tell me without doing any calculations whatsoever, why does it make sense that this melting process is favored, spontaneous, at 10 degrees? It's above its freezing point. It should melt above its freezing point. Was this one favored, yes or no? Yes. It was. Okay, now, That's at its melting or freezing point, same thing. Okay? The only piece of this is that you're not seeing is the process in the reverse direction is also favored, whether you guys are aware of it or not. If you have an ice cube at 0 degrees, yes, melting is going on, but so is the process of refreezing. It's in equilibrium. Okay? So actually, both directions would be favored. Why does it make sense that at -10, this process would not be favored? Because you're below its freezing point. Okay? Now, am I likely to give you something quite so simple on a test? Probably not. But, was doing these calculations difficult? No. No. Okay. So, what might you have to do if you're not necessarily doing a calculation? Okay? First of all, if you have the PowerPoint slides, put stars all around this slide. If you don't have the PowerPoint slides, wherever you're taking notes, put in like capital letters. This is important. This is probably the most important topic in this chapter, or at least I think so. And it says in red letters, don't memorize. Now, can I honestly stand behind you and be like, don't memorize it. Don't memorize it. Stop it. It looks like you're memorizing. Stop it. No, I can't do that. I can't stop you from memorizing this chart. However, if you can explain it and reason through it, it will be a much richer understanding for you. And let me tell you guys something about the AP exam. The AP Chem exam is more and more every year going to questions like explain why ... rather than calculate something. So you need to be able to reason through this. You need to be able to explain it. So here we go. Now, what is this even talking about? This would be giving you information about a reaction. What kind of information? Well, what's delta H again? What is that? Change in heat. And then this is our new one. What's this? Change in entropy. You would be given information about these two entities. Maybe you'd be given actual numbers. Maybe you would just be told the delta H is negative, delta S is positive. It depends on the question. And you would be asked, under these situations, when will this reaction be favored, if ever? We're not going to memorize it. We're going to learn it. So here we go. I'm going to actually start down here at the bottom. Can you all tell me, please, what does a positive delta H value, what does that even mean? It's endothermic. Okay. Well, let's think about what that even means. Heat is required. Heat is like a reactant. Heat is absorbed. Very simple example. In order for a pot of water to boil, you have to add heat. You have to turn the stove on. Okay? That reaction will not happen unless you put heat into the system. Now, guys, does that sound to you, what I just described, does that sound like a process that will happen on its own without any help? An endothermic reaction that you have to put heat in to get it to happen? No. Most endothermic reactions, not all, most, are not likely to be favored. I'm going to put an X there, meaning probably not going to be favored. Probably not going to be spontaneous. Let's look right here. Please put this in your own words. What does a negative change in entropy mean? What's happening? Is it getting messier or is it becoming more organized? It's becoming more organized. Does the universe like that? No. That is also a situation that is not likely to be favored, not likely to be spontaneous. And guys, if you have a situation where you have a double no, not likely, that is a reaction that will never be favored, will never be spontaneous, is never going to happen unless you do something to help it out. There's no math required here. Okay? An endothermic reaction that is becoming more organized will never be favored. Let's come up to the top. Tell me, what does a negative delta H mean? What is that? An exothermic reaction. Think about what that means. We have so much heat, we're giving it away. We're releasing it, producing it. Heat is not required to produce products. Does that sound like a situation that might be favored? Yeah. I'm going to put a check mark, meaning most, not all, most exothermic reactions will be favored. Most. Put this in your own words. What's happening? Positive change in entropy? What's going on? It's getting messier. Does the universe like that?
Yes.
Yeah. So that's a double yes. If you have this situation, this exothermic reaction that is getting messier will always be favored. Doesn't matter if it's cold, hot, you're in the Arctic, you're on the surface of the sun. It doesn't matter. This reaction will always occur on its own without any help. No math required. It's these middle two that are a little dicey. All right, so let's deal with this one first. You guys tell me. Endothermic, likely to be favored, yes or no? No. It might be, but not likely. Getting messier, what do you think? So we have conflicting information here. All right, well, I'm going to make up some numbers here. When you have conflicting information, it's a reaction that can be favored, but it's not favored all the time. And you have to tell me when it is and when it isn't. So I'm going to make up some numbers here. Let's say that the delta H is 2,400 joules per mole, and the delta S is 30 joules per mole Kelvin. Okay, they're both positive numbers. I want you to come up here to this equation we were just using a moment ago, and we're going to do a little mental math. Let's pretend this is a multiple choice question. You don't have your calculator. I'm going to plug these numbers in, and for reasons I will explain in just a moment, I'm going to set delta G equal to 0. I'll explain why in just a moment. 0 equals 2,400 minus T times 30. Don't pick up your calculator. You can do this. What does T equal? 80. Thank you very much. And it's a temperature. What do you think my units are? Kelvin? Okay. 80 Kelvin. All right. Well, guys, that temperature is the temperature at which the process, maybe above, maybe below, we'll have to figure that out, in one place is favored and in the other direction it isn't favored. Now we have to figure out, is it favored below 80 or above 80? We have to figure that out. We're not going to memorize this, right? Right. Okay. Would you guys please pick let's pick a number below 80. Let's just see what happens in that range below 80. Can you guys give me a temperature, a number to plug in there that would be really easy to work with?
1.
How about 1? Sounds good. Let's see what happens in the temperature range below 80. If I plug in the number 1 for T right there, what does delta G come out to equal? 2370. Positive, right? Guys, what does a positive delta G mean to you? Not favored. We just plugged in a temperature below 80 and found that it means it's not favored. So when must it be favored? Above 80. When this says favored at high temperatures, what that really means is it's favored at any temperature above whatever we just solved for. I did not have to do any math here or here. I did have to do a little mental math here. Because it's not favored all the time or never. It's favored at certain places. Okay. Last situation. I'll do a little erasing here so we can get a little clearer. Okay. Exothermic. Likely to be favored, yes or no? Yep. Not definitely, but likely. Becoming more organized. Does the universe like that? No. Here's that conflicting information again. I'm going to choose numbers. I'm actually going to choose the same numbers. I'm just going to make them negative. So let's say that's negative 2400 and this is negative 30. If we come back up to the top, what do you get? Not negative 80.
Still positive.
Still 80. Okay. There's no such thing as a negative Kelvin temperature. Okay. So it comes out to be 80 again. But still, guys, we have to figure out, is the area where it's favored, is it below 80 or is it above 80? Let's choose, again, a really easy number to work with, like the number 1. What kind of a result do you get for delta G if you plug in the number 1 right there? You get a negative delta G, and what does that mean? It is favored. When I say favored at low temperatures, what I really mean is temperatures below whatever you solved for. So here's the gist, guys. You'll have these situations in multiple choice. You will also, and this is the parts that's harder, you will have these situations in free response and they will say, explain why, defend your answer. If you're going to say it's favored at all temperatures, you need to be able to say an exothermic reaction with increasing entropy will always be favored, or something like that. Okay? Now, we're only going to do one more slide and then we're going to stop. Okay, let me explain why I set delta G equal to 0 and what that even means. Okay? So let's just kind of recap here for a minute, guys. What does it mean for delta G to be negative? What does that mean? Favored, okay? What does it mean for delta G to be positive? Not favored. So delta G equaling 0 is like the boundary where you go from being something that is favored to not favored. Delta G equaling 0 means, are you ready? This is kind of earth-shattering. It means you are at equilibrium. Okay, maybe that wasn't so earth-shattering. I thought it was pretty big. Okay? Now, this is the last thing we're gonna do, okay? And you might want to just write this down before you even read this problem. I just said delta G equaling 0 means you are at equilibrium. Well, ladies and gentlemen, if you are going through a phase change at something's, like let's say its melting point or its boiling point, if something is going through a phase change at its melting point or at its boiling point, that is at equilibrium, okay? If you have ice at 0 degrees, you could set delta G equal to 0. That would be okay. So you're going to do this problem, but let's just look at it. It says, for ammonia, the enthalpy of fusion, stop there. Which variable is that? Enthalpy. Delta H, okay. What does that mean in chemistry? It does not mean putting two things, fusing them together. What? Thank you, yes. That is a fancy word that means melting. Okay, so the heat of melting is this. Which variable is this guy? Delta S of melting is that. Will this ammonia spontaneously melt at 200 K? There's your first question. And guys, just to make sure you were paying attention, if you are given numbers and it says, will this happen spontaneously or is this favored, what are you solving for? Thank you. Okay. Part B, what is the approximate melting point? What are you solving for? Not G.
Solving for T.
You're solving for a temperature. Yeah. T is your unknown. You guys take it from there. All right, check it. Okay, now guys, let me say something. Let me say something about letter A. I chose to change into units of having everything in joules. You may have chosen to keep everything in units of kilojoules, and that's fine. If you chose to go with kilojoules, then your answer for part A should be negative 0.130 kilojoules per mole. And that's fine because, guys, if we're supposed to answer the question, is it favored? I don't actually even care what the number is. What do I care about? Yeah, the sign. Is it positive or is it negative? And you can see with my exclamation points, I'm very excited about thermodynamics. Okay? A few people asked, did you need to change the temperature in letter B back to Celsius? No, unless they ask you to. All right. There's one final thing that I want to say about this. Okay? Focus here on letter B. The question gave us some information about delta H and delta S, and it said, what is the melting point? All right? Well, what if the question had asked, what is the boiling point? If you're at the boiling point, are you at equilibrium? Yes or no? Yes. And if you're at equilibrium, you can do that, right? Well, the boiling point and the melting point are definitely not the same temperature. So what would cause me, if the question was, what is the boiling temperature, what would cause this to be a different number? These values would not be the same numbers. Let me actually come back to the original problem here. It wouldn't say enthalpy of fusion. Do you know what it would say? Enthalpy of Thank you. Vaporization. And it would say the entropy of vaporization. And these numbers would be different. Okay? I just wanted to point that out to you. So we will stop here, ladies and gentlemen. I told you we would stop early today. We are done.